Laplace transform, so we can derive these basic formulas. Yeah. All right, next. Yeah, let me just turn off. Yeah. All right, next. Yeah. Look at the formula number 7. Okay, look at the formula number 7. In the formula number 7, we require that n is non-negative integer. Yeah. And I need to change the color. Change the color here. All right. So here we need n greater or equal to 0 and should be integer. Okay. Yeah. All right. Otherwise, think about if n is not integer, how do you define factorial? Right? Only when n is an integer, non-negative integer. Yeah. Negative integer. What's the factorial of negative integer? You don't have it. Okay? Non-negative integer. Yeah. Do you know the 0 factorial? What is the other factorial? Easy, but what is the 0 factorial? It is defined. 0 factorial. It is defined. It looks like 0, but actually it's 1, not 0. Oh, sorry, not 0. It must be 1. Oh, sorry. Why I always put a 0, 1. Yeah. Can you imagine why 0 factorial is 1? Why? How to explain it? 0 factorial. 1 factorial is 1. But 0 factorial also 1. Okay? Yeah. How to understand, right? Yeah. First, let's think about n factorial. Yeah, we can understand in 2 ways. Yeah. N factorial. That's the product of the first n consecutive positive integers. That's the n factorial. All right. Yeah. All right. You can use this interpretation to cover all the positive integers. Yeah. But then when you move to 0, you need to change the understanding slightly. Yeah. All right. When we define a factorial, we use product of consecutive integers, right? Yeah. Yeah. We use that way. All right. Do you have a little bit computer science experience, slightly programming? No? Yeah. So that's why. That's because that background will help you understand the. Yeah. Oh, I don't want that. Yeah. Yeah. Because when you calculate the product, yeah, in computer science, when you calculate the sum and product, the way you do it different. When you calculate sum, you set some variable initial value is 0, right? Yeah. Then sum equals sum plus a new operand, right? Yeah. Keep adding new operand. So this sum variable accumulates the sum. But when you calculate a sequence of product of a sequence of numbers, you set initial value as 1, right? Then you have a second operand, product equals product times, this product variable equals prod times a new operand, okay? Then you can accumulate, right? Yeah. So you can see, for a product, initial value is 1. For some, initial value is 0. Okay? But here, factorial, we calculate product, right? So the initial value is 1, okay? So then we do consecutive multiplication, right? All right. Then, for n equals 1, we do consecutive multiplication of one integer. So it's okay. But when n is 0, we do not multiply a new, because there is no operand, right? So we do not multiply any operand, right? But we use the initial value is 1. So this way is one way to understand why. Yeah. Another way, So that is, So another way, we use recurrence formula. Okay, all right. We introduce a new function f of n equals n factorial. Okay, all right. Then, can we write f of n equals n times f of n minus 1? N times n minus 1 factorial. N minus 1, we use f of n minus 1. Okay? Because in this way, we get a recursive function. Recursive function. Okay, all right. Then, with this recursive function, can you write f of n minus 1 equals f of n over n? Division, right? Divided by n both sides. Yeah. After you have that, can you plug in n equals 1, right? N equals 1. So left-hand side f of 0, right-hand side 1, f of 1, 1 over 1 equals 1. But f of 0 is 0 factorial. So 0 factorial, in this way we can get a 1. Okay? Yeah. So we have these two ways we can understand. 0 factorial is well defined. It is 1, not 0. Okay? All right? But the question here, after we understand, the factorial is defined for non-negative integers. But here the question. Because this t to the n plus 1, when n is not an integer, it is still a power function, right? T to the a function. Yeah, here, let's consider t to some number a. A we can consider as a positive number, greater than 0. Yeah, it's a power function. Yeah, we can still calculate Laplace transform of a power function, right? Yeah. So here, our next question, how to calculate Laplace transform of a power function? This time, a is not an integer. A is greater than 0, but, any real number, positive real number. A can be any positive real number. How to calculate? That's the next question. Okay, all right. Yeah, so let me answer this question first. Yeah, in order to calculate this function, we need to understand, these are the basic formula. Yeah. All right, before I calculate, here I just, copy the table from the textbook. But in this basic formula, look at the formula number 5. That's for a, t power function, positive, a positive, t to the a function, and the Laplace transform, there is a new function. Do you know this function? Have you seen this in calculus a little bit? Yeah, calculus, gamma function. Gamma function at very late state, probably calc 2, calc 3. Yeah, very late part, gamma function. Yeah. to calculate this Laplace transform, we need to use the gamma function. Why gamma function? Gamma function is the generalization of factorial. Okay? Because factorial is only defined on non-negative integers. Gamma function defined on non-integer. Yeah. For non-integer, because factorial does not make sense, so then we define a special gamma function. Okay? Yeah, first, let me talk about the gamma function. Yeah. Laplace transform and gamma function. Okay? First, let me give you the definition of gamma function. You can see its form very close to Laplace transform. Look at this is definition. Okay? Gamma of nu plus 1. Okay? Nu constant. Nu is a constant greater than negative 1. Okay? So nu plus 1 is greater than 0. Yeah. All right. So gamma function is defined as the integral from 0 to infinity, e to the negative t. Yeah. Our Laplace transform e to the negative st. There is s, but here no s. Okay. T that times t to the nu dt. Yeah. You can see closely related. Yeah. Gamma function, Laplace transform. All right. So then, if we apply the integration by parts on that gamma function, okay, yeah. So the first term 0, the second term you can see this integral part just the gamma of nu, yeah, because the t part nu minus 1, yeah, nu minus 1 plus 1, so gamma of nu. Okay, so you get the recurrence relation. Gamma of nu plus 1 equals nu times gamma of nu. Is this recurrence relation similar to that factorial? Do you remember I wrote the recurrence relation of the factorial? Yeah, similar. Yeah, right? Yeah. So this is a recurrence relation. Yeah. So our factorial, we have this, if I use f of n plus 1 equals n times f of n. That's the factorial recurrence relation. Oh, yeah. But this recurrence relation, if we, doing it all the way down, so, so at the end, so actually, at the end you will get a factorial. But for this gamma function, if you use the nu as non-negative integer n, then you get a factorial. So factorial is a special case of the gamma function. Or gamma function is a generalized factorial. Yeah?
So is this generalizing it in the sense that we can use this if it's negative, or is it just generalizing any positive?
So here, generalize, so gamma function inside the parenthesis is positive. Okay? Yeah, because plus 1 is positive, right? Plus 1 is positive. Nu greater than minus 1, nu plus 1, positive. So inside that, the variable part inside the gamma function should be positive here to generalize.
If we were to have -2, for example, it wouldn't work.
Yeah, it won't work. Yeah, good. We will have trouble, okay? When you have negative, your integration by parts break here, okay? The first, because we plug in 0, 1 over 0, right? Yeah, so, yeah, it will break, yeah. So that's why, we require that, yeah. All right. Okay. All right. Yeah. Then look at the definition of gamma function. Yeah. All right. If we replace that nu by a, yeah, this just repeat that. Okay. So we get this. Yeah. The reason later we need to use this formula. So let's put this formula aside. Okay. Yeah. This gamma of a plus 1. Yeah. Yeah. Here we need a positive. Okay? Yeah. Because remember our goal, we want to calculate Laplace transform of a t to the a, right? Power function. Yeah. In that power function, we need that a positive. Okay? Yeah. All right. Now, let's do that. Some trick. All right. Let's calculate Laplace transform of t to the a. Then we plug in the definition, Laplace transform. Yeah. But then, when you see this one, this expression, yeah, the next step is important. Yeah. Next step, we introduce a new variable x to represent the product of s and t. Here, s is positive, right? So we know s is positive. Yeah, s is positive. Yeah. Can you see? We require s positive. Yeah. Otherwise, you can see if s is not positive, if s is negative, e to the negative, positive number, there, it cannot converge, right? Yeah. Only s is a positive number, e to the negative s times t times that the integral converges. If s negative, this whole integral does not converge, okay? If you take integral goes to infinity, it's infinity, okay? It does not converge. So, Laplace transform cannot be defined. Yeah. There is a condition in order to make Laplace transform well defined. Yeah. Later we will talk about existence of Laplace transform. There is a condition. Yeah. Yeah. So here we require the s positive. All right. Yeah. So that we use x to represent the product of s and t. Okay. Then t equals s x over s. Yeah. Here we treat s as constant. Okay. X is variable, t is variable, but s is constant, a positive constant. Okay. When we choose some s there, we never change that s. Okay. Yeah. During the calculation of the integral, we never change that s value. So we treat it as a constant. All right. Next, let's use x variable. Yeah. Substitution, variable substitution. Okay. Yeah. E to the negative x. Okay. One variable. St becomes x, one variable. All right. Then t becomes x over s to then parenthesis to a. Okay. Yeah. But the s is constant. Okay. S is constant. Yeah. All right. So there, dt equals dx over s, constant. Okay? Yeah. All right. Then, because s is constant, we can factor the constant out of the integral. Yeah. So we combine, all the s. Yeah. S to the a and another s. So s to the a plus 1. All right? So we can factor 1 over s to the a plus 1 out of the integral and leave, remaining variable. Yeah, because the remaining terms all contains a variable, so we cannot factor it out. All right. Now you view this integral. What's that? What's that expression? If you look at the form of that integral, what is that number? not 1. Oh, yeah, because although here you use x, we call it a dummy variable, right? If you replace x by t, it's the same, right? Because it's a dummy variable. Okay? Yeah. Can you, after you replace x by t, what's that? Yes. Replace x by, is it this integral? This integral, that's the gamma of a plus 1. Right? Yeah? That's the gamma function, a plus 1. Then you can write the formula is gamma of a plus 1 over s to the a plus 1. See? Yeah. So, yeah, because the gamma function can be calculated, right? Yeah, gamma function, the formula given here, you know, people can calculate the gamma function. Yeah. Although it's hard to give an explicit formula of gamma function. Yeah. But we can use computer to calculate numerically, right? Yeah, because it's an integral. Yeah, for any gamma of a plus 1, a positive number. Yeah, so we can use computer program to approximate the value of gamma function. Yeah, so we treat the value is there. Okay, yeah, whenever we need, we can calculate. We plug in, you know. Yeah, but the integral calculation, you may need a program to find its value. Okay. Not that easy. Yeah, but it's known. We treat it. This is a known number. Yeah. All right. So now we get a Laplace transform of the power function. Yeah, but we need to use the gamma function to represent it. Okay. Yeah. Yeah. All right. Yeah. So after that, so you know a little bit about the gamma function. Yeah. Yeah. So in your calculation, you just leave there. Okay. Yeah.
So is this useful if you have a factorial that you don't want to write out and calculate by hand? You use the gamma function in a computer.
Yeah. Yes, you can do that. Yeah. Yeah, you can do that. Yeah. So that's yeah. But usually factorial, yeah, people would rather keep n exclamation sign because that's easy to understand, right? But if you write gamma of n or gamma of n plus 1, you know, 90-something% of people, they don't know the gamma function, right? Yeah. So you want to make people understand your formula, you know, easier, right? Yeah. So in that case, if it's a factorial, you write factorial sign. Okay. Yeah. You don't use gamma function to make it harder to understand. Yeah. Yeah. But it's correct. Yeah. It's correct. Yeah. All right. Yeah. So now, next we need to look at one important theorem called the first shifting theorem. Yeah. So very simple, but in our calculation, we need to use this theorem quite a lot. Yeah. 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 Many places we need to apply this theorem. Yeah. All right. Yeah. So let's study this theorem first. Yeah. All right. This is the definition of Laplace transform. Okay. All right. Then think about, we replace s with s minus 1. Okay? That's a shift operation. Okay? Oh, sorry. S minus a. A is a constant. A is some, you know, some constant. Okay? Yeah. S minus a. All right. Replace that. Okay. Then we have, if you just plug in, you have this capital F of s minus a. Then in the integral, you need to change that, you know, exponent of that e function. Yeah. Then simplify it. After the simplification, yeah, yeah, inside Laplace transform, you have e term, e to the at times little f function, the original little f function. Yeah, that's a nice property. Okay, so you can see, you can compare capital F side and Laplace transform side. You can see in the capital F side, if you make a shift, a simple shift, yeah, shift operation, minus a we treat as a shift operation, okay, because the graph is a shift. Okay, why people call shift, right? Yeah, because the graph, if you compare the graph of these two functions, one is a shift along x-axis, you know, that a units, yeah, all right, shift to the right, shift to the left, okay, yeah, minus a, so you shift to the right by a units, okay, plus a, you shift to the left by a units, okay, yeah, like that, all right. So at the left hand side, you do a simple shift operation. At the right hand side, you need to multiply that extra e term, okay, e to the at. Yeah, yeah, that function you multiply it to the original little f function. This is the one important property, so we call it first shifting theorem. Okay, yeah, so let me write that theorem formally. Yeah, two parts. Yeah, because when we have a Laplace transform, at the same time we have inverse transform. Okay, so we have two formulas here. Okay, we have two formulas. The first formula, we just, you know, copy. Oh, yeah, I need to maximize that screen, right? Yeah, why? Let you see more space. You know, yeah, larger screen. Yeah. All right. Yeah. Yeah. The first one. But when you have Laplace transform, you switch the sides, right? And the inverse, yeah, you know, this e term multiply original little f function, yeah, this side inverse of capital F of s minus a. Yeah. Yeah. This theorem, very simple, but very useful. Okay? Yeah. So you use it. Yeah. Sometimes when you see this extra e term, yeah, you know, product, yeah, you connect to the shift operation immediately, Laplace transform. Okay? Yeah. If you see the shift, yeah, you connect to that. Okay? Yeah. All right. But you need to, you know, practice to get more experience. Yeah. Example, yeah. Inverse Laplace transform. We need to calculate inverse Laplace transform in this example. Yeah. When we calculate it here, I give you the basic formula so we are going to use in this example. Yeah. All right. The first formula, we start with basic formula number 7. Yeah. So in the, you know, that table 6.1, yeah, we have these formulas. This one, now remember we apply the first shifting theorem. You multiply that e function, e to the at. There, at the right hand side, you need to replace s by s minus a. Yeah, that's simple. Okay? So, and the second one, you do the same thing on the sine function. Yeah. So number 12. Yeah. So if you take Laplace transform of this function, you get that. Okay? All right. Yeah. So here I put the first shifting theorem here. Okay? So you can compare. Yeah. All right. Then let's do calculation. This example. Given. Yeah. So the Laplace transform is given. Okay? Yeah. That means this is capital F, right? Yeah. Based on our notation, this whole fraction corresponds to our capital F of S. All right. Then you need to find little f. You need to find inverse Laplace transform of that whole fraction. It looks pretty complicated, that fraction. Yeah. Here we need to use these formulas. Okay? These two formulas. All right. Yeah. So first, we need to do some decomposition. We need to make the structure of that fraction more friendly. Okay? More friendly. Yeah? Yeah, containing the, that shifting structure, okay? Shifting format, yeah? So let's do that part first. Yeah. Okay? All right. Because when you look at the denominator, s squared plus 2s plus 1, you get s plus 1 squared, right? Yeah. So s plus 1, yeah. Yeah. All right. Then the numerator, because you need s plus 1, okay? All right. So when we write that, s plus 1 squared plus 400 denominator. Numerator, because you need the same s plus 1 term in order to apply the above formulas. Yeah. So 3 times s plus 1, but you need to change the constant part to 140. Okay? After that, in order to apply the formula, there is one step you need to do. Yeah. Linearity. Yeah. Remember, for Laplace inverse transform, we also have the linearity property. Yeah. Laplace transform, we have the linearity property. Yeah. Laplace inverse transform, we also have the linearity property. Okay? So here we need to apply the linearity property on inverse Laplace transform. So we can split into two terms. Okay? The first term, because we split. Okay, the numerator we split in the middle. Yeah, the first term minus the second term. All right, the first term, the constant, we can take it out. Okay, linearity principle. Then minus second linearity, because we need to leave 20. Why? Yeah. So some of you may feel, why we leave 20 here, not 1? The reason is we try to fit the format of that one. Okay? Yeah. Yeah. That one, in order to apply the formula, the numerator should be omega. Yeah. Here, because omega is 20. Okay? From the denominator, omega should be 20. So the numerator should be that same omega number. So that's why we need to leave 20 in the numerator. So we only factor out 7. Yeah, 7 out. Yeah. Then we are ready to apply the basic formulas. Okay. The last step, the first term. Yeah. This time a equals -1. Right? Yeah. Because plus 1. That one tells us minus a, minus -1, okay? Negative. So e to the -1 times t, that cosine omega t, right? Yeah. So second one, 7 times, yeah, also -1, okay? Yeah, -1 times t, and the sine omega t. Yeah? That's the answer. Yeah, that's the way to find inverse Laplace transform using the basic formulas. Yeah. So you need to formulate or transform. Yeah, but here the transform, we don't want to, get confused. Yeah. So you need to rewrite your formula following certain structures. Yeah. The structure you need to target the structure used in some basic formulas. Yeah. when you manipulate your formula, so there is a target, okay? Yeah. Moving toward the forms of some basic formula. Yeah. Then apply the linearity principle, okay? Linearity property. Yeah. Let's say linearity property. So you can factorize constant. Yeah. Yeah. But it's not, yeah, do not factorize all the 140 out, because then you don't have omega, okay? Leave the omega. So you need to, you know, yeah, you use the same form in the basic formula. Yeah. All right. That's the first example. Yeah. Yeah. You need to practice. Okay. Yeah. Yeah. All right. Next. Yeah. C.2. This time, existence and uniqueness of Laplace transform. Yeah. Now we need to consider, we need to make sure when we apply Laplace transform, there is no problem. No. It's legal, okay? So it's not garbage, yeah, because if Laplace transform does not exist, all your calculation is garbage, right? It does not converge. Okay? So when you do some work, you know, all your integrals, you know, never converge. Yeah. Yeah. So G.2. Yeah. We will check these conditions. Yeah. All right. Condition pretty simple. Yeah. All right. Existence theorem. Yeah. Yeah, but the first question, yeah, because sometimes people may argue, so why we need to know the existence of Laplace transform of a function? Yeah, I explain a little bit, yeah, but some people, they make argument like this, yeah, 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 given an ODE, yeah, given an ODE. They just want to apply Laplace transform on it to find a solution. Yeah. So they don't worry about the existence or not. Yeah. Then, how to avoid you work on some garbage, right? Yeah. So their argument is like this. After we find a solution of ODE, yeah, because after you apply Laplace transform, you will get a solution of ODE. Yeah. In order to see your solution is garbage or not, you can verify. Yeah, you plug in into the original equation. If it works, you know, satisfy original, then yeah, you get a valid solution, right? Yeah. So their argument is like this: even if you do not check the existence of Laplace transform, yeah, your goal is find the valid solution, but if you apply a Laplace transform, you can find a valid solution, then it's good enough. Okay? Yeah? That's their argument. Okay? Yeah. 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 It makes sense, right? It makes sense. Yeah. Yeah. Many people, actually, even mathematicians, some famous many famous mathematicians, they did things like this when they developed some new formulas. Yeah. Euler doing things like this. Euler. Okay? Yeah. And he did a lot of calculation without worrying about, you know, if the calculation is legal or not. Okay? Yeah. But then he derived many fancy formulas. Yeah, you know. After that, just verify if the formula makes sense. Yeah, yeah. Many mathematicians take this approach. Yeah, to discover new formulas. Yeah. All right, but for us, yeah. Although you know this is one way. Yeah, yeah. People can take in this way. or we can say practical way, right? Some practical way, all right? It helps us to understand Laplace transform better. Yeah. Because we still we want to get a better understanding. Yeah. Theoretically, we want to see if the Laplace transform exists or not for a particular function. Yeah. All right. That existence theorem for Laplace transform. If little f function is defined and piecewise continuous. Yeah. So you know piecewise continuous? Yeah, piecewise. Yeah. So it's slightly weaker than continuous. Continuous, you cannot have any discontinuity, right? Piecewise, yeah, so the whole curve, you can divide it into several pieces. Each piece is continuous. Yeah. But between two adjacent pieces, there is a jump. Okay? There is a discontinuity point. Yeah. So that's the piecewise continuous. Here you can see, for this existence theorem, you only require that little f function piecewise continuous, weaker than continuous function. Yeah. On every finite interval on the semi-axis t greater or equal to 0, and satisfy, equation 2. Yeah, equation 2. Yeah, so you know the Laplace transform definition. Okay, all right. Yeah, and some not that. Yeah, equation 2. Yeah, I will put aside. Sorry, equation 2. Some inequality. Yeah, I will. Yeah, write equation 2 here. Okay. Yeah. So what's that equation 2? So I put it here. Okay. This inequality. Yeah. For some constant capital M. Capital M should be positive constant. Yeah. Capital little k a constant. Okay. Yeah. Yeah. Even negative value is okay. Yeah, positive and negative, both okay. Yeah, little k. All right. Then the Laplace transform exists for all s greater than k. That's the existence theorem. Yeah. And in this graph, that's the piecewise continuous function. Yeah. The meaning of piecewise continuous function. Okay. Yeah. So if you can break the function into several pieces. Each piece is continuous. Yeah, yeah, yeah. So then you can check this theorem. Yeah. So the condition, actually, this condition, the bound, you can see it's a bound condition, right? It's a bound condition. Yeah. It's very, very easy to satisfy. Yeah. This bound condition is very easy to satisfy, okay? Because the bound, right-hand side, capital M times e to the kt, k could be a positive number, right? When k is a positive number, this e to the kt is it is an exponential function. Exponential function increases very fast. Yeah. So you use a function that is very large, exponential function, as the upper bound. Then it's easy to get satisfied, right? Yeah, it is easy to get satisfied. Yeah, yeah. All right. Yeah. So then, proof. Here I write a short proof. Okay, the short proof. You want to show, you take the absolute value of this definition of the Laplace transform. If it's less than infinity, okay, less than infinity, if it converges, then it exists. Okay, so we want to show this integral converges. Yeah. All right. Let's. Yeah. So put the absolute value inside the integral. Yeah. So less than or equal to. Yeah. Yeah. Inside, now you can use the upper bound estimate. Okay? Yeah. After use the upper bound, M, K, yeah, S, yeah. Then if S greater than K, you can find its integral. M, capital M over S minus K. It means it converges. Okay? It converges. Yeah. Yeah. When S greater than K, so the negative term if you look at the absolute value, the negative part is greater than the positive part. Okay? So after you put them together, you get a negative exponent. Then convergent. Yeah. If it's not negative, think about if the E function, the exponent is not negative, then this integral does not converge. Yeah, very easy to see that. Yeah. 0, that does not converge, right? If 0, capital M, you take integral to infinity, it does not converge. Then if a positive going larger and larger, it does not converge. Okay? But negative, you can find it. Integral. Yeah. So it converges. Yeah. All right. So it's an easy proof. Yeah. All right. Uniqueness. Yeah. So after existence, you want to see. Now think about. Suppose we have two piecewise continuous functions, f1, f2, little f1, f2. They happen to have the same Laplace transform. Yeah. Yeah. Because uniqueness, we want to see the case when Laplace transform of little f1 and little f2 the same, can we get f1 equals f2? That's the uniqueness. Okay? Yeah. If we can, if their Laplace transform are the same, this fact implies these two functions must be the same. Then we say the Laplace transform has this uniqueness property. Okay? Yeah. All right. So for the uniqueness, in order to make uniqueness property true, available, now you need to change to continuous function. Okay? Yeah. Not piecewise. Okay. Piecewise too weak. Yeah. Piecewise, if you use piecewise, then f1 equals f2 except at discontinuity points. Yeah. f1 equals x2 except those, finite number of discontinuity points. Yeah. In that situation, f1 equals x2, other than finitely many discontinuity points, people call it essentially the same. Okay? These two functions are essentially the same. Yeah. Because those scattered points not very important. Okay? These discontinuity points, if you look at the integral, the value in those finitely many points, they do not change the integral. They do not change the integral. Okay? Yeah. Yeah. So that's why people call, if two functions all the same except at finitely many points different, so people call it essentially the same. Okay? Not completely the same, but essentially the same. Yeah. But if these two functions are continuous, two continuous functions, then you do not need to use that essential. They must be the same. Okay? They must be the same. Yeah. Yeah. But how to prove it? It's not that easy. Yeah. 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 So here we do not do it. Yeah. Yeah. Our textbook gives the reference. Yeah. Yeah. So you can follow the reference. Yeah. All right. Yeah. So now you understand the existence and the uniqueness theorem for the Laplace transform. Yeah. All right. So these two theorems help us understand Laplace transform better. Okay? Yeah. All right. Yeah. So, yeah, we're near the break time. Yeah. Let's take a break. Okay? Yeah, because we are going to start a new topic: Laplace transforms of derivatives, then integrals. Yeah. Let's do these two topics after 10-minute break. Yeah. 10-something minute break. Yeah. So we start the second half at 7:10. Yeah, still 7:10. Okay. All right.